Hello and welcome. In this video, we are excited to introduce the first version of the VEX Generation Toolset, which is a tool developed in collaboration between the Apache Software Foundation and OpenRefactory, and which was funded by the Alpha Omega Fund. Before we dive into the toolset, let's quickly recap what the VEX document actually is. VEX stands for Vulnerability Exploitability Exchange, and it's becoming an essential component in modern software security. A VEX document helps answer one of the most important questions in vulnerability management. I know that my software includes a component with a known vulnerability, but is that vulnerability actually exploitable? In many cases, the answer is no, because only a small fraction of a component's functionality is ever used by an application. VEX provides a formal way to express that. Let's look at the context. The number of public vulnerabilities unfortunately doubles every couple of years. Since 2015 until now, it has almost grown 8 times. With this growth, large applications spend fewer and fewer days in a completely vulnerability-free state. So trying to constantly upgrade components preemptively simply doesn't scale. Instead, we need a way to understand reachability and exploitability. Is the vulnerable code even used? Is it reachable under normal conditions or abnormal conditions? That's exactly the problem that the VEX Generation Toolset is designed to address. Assessing exploitability is a multi-step process, and that's why the VEX Generation Toolset provides free microservices that can automate the workflow end to end. We start with a software bill of materials, an SBOM, that identifies all of the components that are included within an application and is produced by tools distinct from this toolset. Once we have an SBOM, we determine which of those components contains a known CVE. We use a Java call graph tool to find all of the calls from the application to those vulnerable components. In parallel, we enrich the CVE entry using the root cause service to extract the actual functions or methods involved in the vulnerability, going beyond the intentionally vague CVE descriptions. Finally, we need to present the call paths to developers. This allows human reviewers to evaluate contexts, validations, and assumptions in the code. These 3 open source components are stored under the GitHub organization named VEX Generation Toolset. That can be found at the URL www.github.com/VEX-Generation-Toolset. The Java call graph component is in the Java call graph repository. The root cause is in the root cause service repository. And the VEX Generation components is in the VEX Generation Service repository. From this overall view of the process, let's show an example. We'll be generating a VEX document for an artifact used by Apache Solr version 9.10.0. We have stored the SBOM in the SBOM folder of the call graphs metadata repository. Here is the SBOM for the Solr 9.10.0 project. Now, for each dependency inside the SBOM, we shall create and store the call graphs in the call graph metadata repository. To do that, we have to access the source code for each item named in the SBOM. Let's see how the entries are stored. We'll use the entry for netty_buffer as an example. The entry in the SBOM gives us the PURL. It also specifies the group, the artifact, and the version, also known as the GAV format. This reference is to the binary version of the package, and we need to map it to the source. We semi-automatically create an entry inside the call graphs folder for each of the artifacts specified in the SBOM. It will specify where to find the source code. The entry is stored in a file hierarchy where there is a folder with the name of the group and another folder with the name of the artifact. So for netty_buffer, this entry will be in the io_netty folder, which is the group, and then inside the netty_buffer folder, which is the artifact name. Let us look at the location.json file stored there. It specifies where the repository is in GitHub. It is in the netty organization, with the repository name being netty. The tag is also specified, which is stored as a template. The call graph tool will take the version name and replace the %s in the template to get the tag. So, for the 4.2.6 final version, it will be looking for the tag netty-4.6.final. The relative path is also specified. This becomes relevant in the case of a monorepo. In this case, the netty buffer package is in the buffer directory from the top directory. Note that this mapping process is semi-automatic at this point, but it is a likely candidate for future automation. With all of this information, the call graph generation step, which comes next, will be able to find out where the source code is located. Now we can begin the call graph generation. The call graph generation is done ahead of time for a project. This is like preparing for the storm. Call graphs are generated by Java Call Graph, an Eclipse RCP application published as a Docker image on GHCR. It will get the source code location information from the location.json files that we had created earlier. To generate a call graph, you will need to specify the source code folder mounted as workspace source. It supports most project structures automatically, like Maven, Gradle, and multi-module setups. You will also need an output folder mounted as workspace result, which will contain the generated JSON. The output is a caps lock-inspired call graph format. Since call graphs can be reused, we generate and store them centrally in call graph metadata using a GitHub workflow called Generate Call Graph. This workflow is stored in the .github workflows folder of the call graph metadata repository. We have a script that will trigger the call graph generator tool on all the dependencies from an SBOM file. This script has only one input, which is the location of the SBOM file. It will get the group, artifact, version, that is the GAV coordinate from each of the dependencies, and trigger the GitHub workflow. The GitHub workflow takes the group, artifact, and version of the GAV coordinate. It will find the location.json file in the appropriate folder and use that to get the source code. Here is the script running, and we see that the GitHub workflow is triggered for each of the dependencies. Here are the GitHub workflows. Let's look into one of them. You will see the Java call graph tool running on the source code. After the call graphs are generated, the GitHub workflow creates pull requests to store the call graphs in the call graph metadata repository. The call graphs are stored in the same group and artifact folder inside the call graphs directory. For the netty buffer version 4.2.6 final, we go to the group folder, which is io.netty, and the artifact folder, which is netty buffer. This is where we saw the location.json file before. We store the call graph in another JSON inside the 4.2.6 final folder. Things get interesting when new vulnerabilities arrive. In our test deployment, we have created a fork of Apache Solr and have created a workflow there. We connected the root cause service to every Dependabot pull request. Here is what happens. A Dependabot PR arrives identifying a new CVE in our Apache Solr fork. We parse the Dependabot metadata to gather all the dependency versions. For each of them, we cross-reference a vulnerability database, GitHub advisories, to find if the old versions were affected by this new CVE. In this case, only one dependency was affected by CVE-2018-1339. For each vulnerability, we run the root cause service, which is an AI agent that looks for the vulnerable function or method in the links provided with the CVE. The agent's input is a simple JSON, and it outputs a JSON. It requires an API key. Some of them are freely available, GitHub token and VD API key, while others require a paid LLM provider subscription, Google API key, OpenRouter API key. So this is the part where you have to use your own API key. The corresponding root cause analyses are triggered in the call graph metadata repository using a simple generate root cause workflow. The workflow takes two inputs, GAV coordinates of the artifact and a CVE number. Once the root cause data is generated, it is contributed back to the database as a pull request. It is stored inside the vulnerabilities folder under subdirectories named by year and by CVE number. The contents of the PR contain all the data of the CVE and additionally contains the function or method that caused the vulnerability. The final component, the VEX Generation Service, combines everything: the enriched vulnerability details and the call graph for the affected project or module. This is why the input of this service is quite complex. We need the list of vulnerable methods, the possible paths in the dependency tree from your application to the vulnerable artifact, and for each node of each path, the URL of the pre-computed call graphs. We provide a script that generates this input using the SBOM of the application, the GAV coordinates of the vulnerable artifact, and the CVE ID. Once we have this input file, we can run the VEX Generation Service. The service outputs for each element of the chain, in this case, Solar extraction to Tika parsers, to Apache MIME4j, to DOM, to Apache MIME4j core, a human explanation as to whether or not the vulnerability is reachable from that artifact. In this case, the vulnerability reaches up to Apache MIME4j DOM, but is no longer reachable in the next element of the chain Tika parsers. In the output.json file, we have a ready VEX statement in the VEX key that contains the same information in a machine-readable form, Cyclone DX. This initial workflow is intentionally kept lightweight and broadly compatible, designed to integrate with any GitHub project regardless of its CI/CD setup. As the VEX Generation Toolset matures, we will introduce more specialized workflows tailored for large ecosystems. In particular, we plan a deeper integration with services like Jira or Renovate bots to support complex projects such as Apache Solar. So thank you for watching. We hope that this overview helps you to understand how the VEX Generation Toolset can make vulnerability management more actionable, efficient, and infallible.